Yes, when I was 10 years old, I used to live in Shepherd's Bush in West London, not that far from here. And every Saturday afternoon, I used to go to Shepherd's Bush Market. You see, I was very keen to see what people were selling, what they were buying, but most importantly, what they were throwing away. Because very frequently among the rubbish, I could find something useful, for instance, wooden boxes from which I could make a cricket bat. But every Saturday afternoon, there was a very strange man. He was completely bald, and he was selling medicines. He was selling medicines in the form of purple tablets like this. And he told everyone that these tablets were very good for you because they could cure you of any disease, whether you had a headache, a toothache, muscle pain, neuralgia, nostalgia, you name it, this medicine would cure it. So people were very fascinated to actually be able to buy this medicine. And they wanted to know why they should buy it. And he said the reason why this medicine was so particularly good and other medicines were bad is because this medicine does not contain any acid. And everyone knows that acids burn. And he had some examples to show people. He had some common medicines displayed on the table outside in the open air, and he showed these medicines to people and told people how evil they were. He had, for instance, Seidlitz powders used for stomach complaints, which contained tartaric acid. Acids burn. He then had some Andrews liver salts used for indigestion. They contain citric acid. Acids burn, he would say. And then he had some aspirins used for headaches and many other purposes. And if you read the label here, they contain acetyl salicylic acid. Acids burn. And he said, please allow me to demonstrate to you the awful damage that these medicines can do, which contain acids in your stomachs. And he had a little table, and on the table he had a tin mat, a sort of a thing, and there was some crystals on it. And he put the aspirins on the crystals like this. And then he said, when you are suffering from a headache or toothache or something, it is entirely possible that you may also have a sore throat. And for that purpose, you may take some syrup. So he had some Sanatogen baby syrup, cough syrup, which is rich in glycerine, and he poured some of that on. And then he said, furthermore, he said, you may take some water. You may like to drink some water with your medicine. So he sprinkled some water on, and he said, watch carefully, because I'm going to show you how this horrible medicine containing acid could start to burn in your stomach. And as the man was talking, as he was talking, suddenly the whole thing burst into flame. People were absolutely terrified of what the consequences would be of taking such a medicine. And do you know what they did? They put their hands in their pockets and they pulled out £5 which was a lot of money in those days, and they used to buy his medicine. Now, as a 10-year-old, I was very fortunate because to start off with, I was never ill. Even more fortunate still, I didn't have any money, so I couldn't buy it in any case. But ever since I had been a very, very small child, I had developed a serious psychological problem. This was a secret and passionate obsession with fire. Now, my parents, and I could not believe how it was possible for this man to make fire out of medicines and water. Now, when I was 8 years old, my parents had bought me a chemistry set. I have here the exact chemistry set which they bought me. It's a K chemistry set, and it has some wonderful instructions and wonderful experiments. And indeed, I used to do these experiments, and I used to mix the chemicals together in an attempt to satisfy my passion for making fire. But alas, this was not possible. I made color changes, I made fizzes, pops, and I made smells, but I could not make fire. So I decided that I would try and do this experiment which this man was demonstrating. I watched it for several Saturdays, and I then decided I knew where I could get the aspirins from Boots the Chemist in Uxbridge Road. I knew where I could get the Sanatogen baby syrup, Boots the Chemist in Uxbridge Road. The water came out of the tap, but I didn't know what those mysterious crystals were, what that powder was that he had. So I went along, I decided I had to find out, and I did the best thing possible. I went along to Shepherd's Bush Library, and I borrowed a book which was called Chemistry Magic, very similar to this book, which comes from exactly that same time. And using that book, I read all the recipes and mixtures which people used in order to make things catch fire. And there was one substance which seemed to fit the bill, the description of what was down there. It was called potassium permanganate. So, together with the other ingredients, I managed to purchase potassium permanganate as well in Boots the Chemist in Uxbridge Road. I set up this experiment in my mother's kitchen at 44 Stanley Road, Shepherd's Bush, London, W12. And lo and behold, within a few seconds, the greatest moment of my life, I had made fire using medicine and water. Now, that successful experiment, dear children, set me off on the greatest path of discovery and voyage that I have been able to do, and that is to do chemical experiments every day of my life. And that's what I've come to tell you about today. Chemistry, you see, is the science of substances and how they turn into different substances. And very frequently, we can recognize a chemical change, that a new substance is being made because there is a change of color. And here I'm pouring for you what appears to be water from one flask to another, but of course it is obviously not water because I am making a new substance, and this is being shown by the fact that there is a color change. Now, chemists are scientists who have learned to understand these changes, and they have put them to great use for the benefit of mankind. In today's world, we have a huge number of substances which are so useful thanks to the discovery of the chemists, whether these are plastics, pharmaceuticals, whether they are washing up detergents, whether they are agricultural products, explosives, fuels, a vast range of substances that we use on an everyday basis. Chemistry has played a huge role. So here I've just demonstrated for you some examples of chemical changes occurring in water. And if you don't mind, I will be moving things around a little bit because of the space facility on this bench here. Now, what I wanted to show you next is something which I popularly among magicians is called magic rainbow water. And the reason is because it can change to all the colors of the rainbow, we hope, which I'm sure you all know are red, orange, yellow, green, blue, indigo, and violet. And I'm going to attempt to make some of these colors for you in front of your very eyes. But I do have to tell you that this, of course, is not magic. This is chemistry. But it is a particularly interesting reaction because in this particular liquid which we have here, it's possible to get all 7 colors of the rainbow just by swirling it around and adding tiny amounts of different ingredients. Now, I will tell you exactly what it is because I said this is not a magic show. What we've got here is actually called universal indicator. And that is an indicator which can show us different levels of acidity or alkalinity. These are substances which have many applications on an everyday basis. And this particular indicator is so good because it shows us 7 different levels, 7 different colors. And as I said, I've just gone through from orange from green through to yellow to orange through to red. And now you see I am now going back again, and here we have a beautiful yellow color. And you know what? I can't predict exactly what color, but in the first few instances, I was adding an acid to make the acidic colors of universal indicator, which go on to the yellow, orange, and red scale. And I'm now adding a strong alkali, which is sodium hydroxide, which is the basis for making soaps, for instance. And I continue to add a few more drops, and I'm trying to go through the range of colors. As I said, this should probably end up with a little bit of a green. And there is a little bit of luck involved in determining exactly which color I end up. But if I add the appropriate amounts, I should manage to get a blue, I hope, an indigo, which is somewhere in between a blue and a violet. And hence you can see people like to call this magic rainbow water. But as I said, it's neither magic nor rainbow, but there are certain similarities. And if you don't understand it, and that's the way science has evolved, before people understood how changes occurred, they used to refer to changes in nature as natural magic. How do volcanoes work? How does lightning flash, etc.? Until scientific thinking was established, based on experiments, people used to only have ideas. And today, I intend to show you in front of your own eyes using experiments which you cannot refute because you have seen them. I'm just going to go to try and get a little lighter color before I move on to my next experiment. Now, here I've demonstrated then for you some examples of chemical changes just by mixing liquids together and getting the color to change, and therefore making a new substance. But you can't just mix together any two chemicals and say, oh, look, there's a chemical there, made a new substance. It doesn't work like that, you see. One of the most important things that you have to understand with chemical changes is that they are always involved with an energy change. And there are different types of energy. That was energy of mixing. You can have heat energy, electrical energy, light energy, mechanical, kinetic energy, and in this most curious experiment here, even musical energy. Watch carefully as I play in the key of D minor. I'm not here. I am merely here. Please, children, I am merely here to explain for you the principles of science. Applause, we can wait at the other end of the spectrum. So, what I have said, why does this work? Well, because you see, when I play the violin, I am generating musical frequencies which have special functions. They have harmonic vibrations, and the energy is projected in an organized manner, interacting with the molecules which are all vibrating, strike up the sympathetic resonance frequencies, the activation energy is overcome, and the reaction takes place. So that, in a nutshell, is the summary. Now, what I've done, I've showed you an experiment with magic medicine. I've showed you some experiments with magic water, we could say. And now, of course, I'm moving on to my favorite topic, which I've told you, which is, of course, fire. And I intend to show you some experiments. In which we look at some different types of fire and explain how the chemist has used his knowledge, or how chemists have used their knowledge, in order to enhance our understanding and our use of fire. Now, here I have a candle which is burning. Now, people have been burning candles since the earliest of times. A candle contains wax. It's a mixture of what we call hydrocarbons, and it gives out a very, very pleasant flame indeed. It is modestly bright. There is a wick going through the middle, and the wax melts where the wick is burning, and so the wax gets sucked up the wick and then changes to a gas and burns as a vapor at the thing. And this is a yellow flame, you see. Now, what I wanted to do is just to show you some other examples of flames and how the science of chemistry has learned to exploit these flames for our benefit or even for our enjoyment. Now, the first one I'm going to start off with is something which is very popularly described by magicians as magic volcano powder. But of course, it's neither magic nor is it a volcano, but it does resemble one. Now, if you were to look at that, and you were to say, oh, that looks very nice, it's an orange powder, it looks just like sherbet, etc. But actually, because this is a chemistry lecture, this is not a magic demonstration, I'm going to tell you exactly what it is. It's called ammonium dichromate, and one of the most important things that you have to know when you do experiments or when you handle materials is to know what the safety procedures are. And if you look at the safety symbols, the warning or the hazard symbols on ammonium dichromate, then you'll see here there's a flame burning, which tells you it's an oxidant and it will make things catch fire. A skull and crossbones tells you it's a deadly poison if you ingest it. There's a picture of a liquid being poured onto a hand and the hand is burning. That tells you it's highly corrosive. And finally, a picture of a person which seems to be having a heart attack or something. That's actually the symbol for a carcinogen. It causes cancer. So in a nutshell, this is a most unpleasant substance. However, it does undergo a very beautiful chemical reaction, as we describe a thermal decomposition, in which it really does resemble a miniature volcano. So I'm going to set this on fire. I'm going to apply some heat to it, and I would just like you to enjoy this miniature chemical volcano. As I said, some people like to describe. Now, for this purpose, it would be good to have the lights dimmed or even entirely switched off, but very gently, because the honest truth is it does take a little while to get going. There it is. Please watch carefully. Now, it does take a little while. There is our chemical volcano beginning to spring into action. And what you'll notice, it looks like a crater with lots of ash and sparks coming forth, you see, in this reaction. Now, the chemical name for this type of reaction is a thermal decomposition. We are breaking down the ammonium dichromate into simpler substances. Could we have the lights back on, please? And let us look to see what has become of our orange powder. You will notice some steam rising. This is a most unusual type of reaction, you see, because there is no smoke produced. What you see is genuine steam. It's water vapor. You will not smell anything as a result of this. And furthermore, you'll see there's been quite a lot of hissing. Now, the reason for that is there is also a gas produced in this, which actually is part of the air. It's nitrogen gas. So what it's making is totally and utterly harmless. Such is the power of chemical changes that what started off as an orange powder ammonium dichromate has been turned by the process of thermal decomposition into chromic oxide, which is totally harmless, which is what this is, plus water vapor and nitrogen, which is found in the air. So this then is just an example of another type of chemical change. But I said, as I did tell you, fire is my great passion, so I'll be showing you a few more of these. Now, the next experiment I wanted to show you in connection with fire concerns a substance which we use on an everyday basis, but we seldom think actually or perhaps understand what we use it for or how it works. And this is a substance which I have here. It's called petrol. Now you will say, well, of course, I know what petrol's used for. You put it into the motor car and you drive the car forward and it goes forward. Now what I wanted to tell you is that petrol actually is not a modern invention. The motor car is a modern invention. The motor car has only been around for about 120 years, but petrol and substances similar, I won't say exactly petrol, but substances similar to petrol have been known for thousands of years. And the reason being is that out of the ground in certain parts of the world, there oozes a black oil. We call it crude oil today. In the same way that coal is found in the ground, oil also oozes up. And many hundreds or even thousands of years ago, people had learnt, they had observed this oil burning, and they had been able to extract it or burn it with a useful purpose in various lamps which they used to have. And we have found these lamps have been discovered by archaeologists. There were three types of oil that people used to burn: mineral oil, vegetable oil, or animal oils. And this is an example of a mineral oil. Now, if you don't mind, in order to show my demonstration with petrol burning, I do need to do a little bit of tidying up. And as you see, the ash there has made a little mess, and we are always prepared for these things. And I'm going to just sweep the ash into a bin, which I have around here, in order that I can prepare my bench for the experiments with petrol. So, I have now efficiently organized my mat here, and I wanted to show you, first of all, how petrol used to burn, or how people used to observe petrol burning for many, many hundreds or even thousands of years. And I'm going to do this. Now, petrol, of course, is very dangerous, so we have the flammability sign, the toxic sign on it, and we have to take great care when we burn even the tiniest amounts of petrol, because it is very, very flammable. And that's, of course, why it's so useful as a fuel. So I'm going to start off here, taking a small quantity of petrol in with my tea pipette here. I'm going to place it onto my fireproof mat, and then I shall set fire to it. Now, once I've set fire to it, I'm going to ask you the question, do you think that this is the way that petrol burns inside a motor car engine? Please watch carefully. I'm about to set it on fire here. Et voila. Now, please look at this flame. Do you think that would make a car do 100 miles an hour down the motorway? No. Just look at the smoke. Yellow, smoky flame. Now, let's look here, children. Wood burning, yellow, smoky flame. You can't see, but it's smoky. Petrol burning, yellow, smoky flame. Candle burning, yellow, smoky flame. Now, to the chemist, that means, and I'm sure you can all agree, there is something similar about. And the similar thing is this. They all contain the element carbon. Carbon is very important. It's what this soot is made of. And I will show you, I can make some of this soot catch here, you see, onto our white surface there. I can wave my white basin here and show you soot collecting there. It is the same element, carbon, which is present in all of these. They have a similarity. You can't dispute that because they're burning in a similar manner. Now, that carbon, of course, is charcoal or soot. And just for your information, candle wax is made up of a mixture of compounds called hydrocarbons. Petrol, too, is a mixture of hydrocarbons, but it has smaller molecules. And wood is actually a carbohydrate. It also is slightly different, but nevertheless very similar in terms of combustion. Now, what I wanted to show you is how the chemist has enabled the fuel petrol to burn much more efficiently, and therefore how it burns inside a motor car engine. Now, for this purpose, I have bought a model of the inside of a motor car engine, and it's a tin can like this. Now, the reason why I've got a tin can like this is because inside the shape of a tin can is a cylinder. Now, inside every single motor car engine in the world, there are shapes like this which are called cylinders. And that is where the petrol burns. That's where the fuel burns. Inside the cylinder is a very tightly fitting piston, which goes up and down inside the cylinder and is connected to a crankshaft which makes the engine go forward. However, I don't have a piston. I have a lid which fits on very tightly. However, for those of you who'd like to know, this is a piston from a real motor car engine. Every single motor car engine, lorry engine, bus, van, whatever burns a fuel, and they're called internal combustion engines, will have these things fitting very tightly inside cylinders, and they go up and down in a reciprocating linear motion, which by the genius of the engineer is converted to rotating motion to make the up and down movement to make things go round, and then the car engine can make the car move forward. So, what I'm going to tell you, that in a motor car engine, of course, the fuel goes in and then is ignited. Now, just for your information, inside a motor car engine, in petrol engines, we ignite the fuel with a spark plug, an electric spark. It's like a little miniature electric lightning flash. But in today's experiment, I, of course, will be igniting it with, there's a hole in the bottom here, there's a hole in the bottom there, and I shall be applying my light there. Now, what I wanted to tell you, and this is the key bit of information. If I were to ask you a question now, what is in this tin? You would be perfectly entitled to say, why, there's nothing in this tin because it was full of paint and now it's no longer full of paint. Of course, that's a correct answer. But from the point of view of combustion, from the point of view of burning, it is full of a most important commodity. And that, of course, is all around us. It is air. this tin is full of air, and I am now going to show you how the petrol burns differently when it is allowed to go inside that cylinder. So we're going to now take our petrol here, we're going to take our teat pipette, and we're going to take pretty much the same amount, even that, just literally a few drops of petrol like that, and we're going to squirt them inside there. Now then, what we're going to do is put the lid on tightly, because the piston fits very tightly. There we are. Just make sure it's on properly, because the piston fits very tightly into the cylinder of a motor car engine. And I'm going to now hold this tin for just a few seconds. Now, while I'm holding this tin, the petrol which I put inside as a liquid is undergoing a most important change. But it's not a chemical change. It's not burning. It's not changing into a different substance. It is actually undergoing a change of state. The petrol went in as a liquid, and now, after a minute or so, it has evaporated, and it has turned into a gas. And I will smell it. That smells pretty strong to me, and therefore that means that we shall be ready to conduct our next experiment. That means the petrol has evaporated and turned to a gas, and this is the important bit. It has now become fully mixed with the air. It has formed what we call an homogeneous system. And if we now apply our light to the bottom, please watch carefully and see if you can spot the difference, the color of the flame, or indeed the effect which is achieved when it catches fire. And there you are. As you see, I didn't quite see what happened, but the lid went high into the air. No, please, I am not here. Dear ladies and gentlemen, do you clap every time you drive a car? No, but this is what all your clap. Now, I clap when I drive my cars because I fix them, you see. I drive old baggers and I have great fun driving them. And so I do have a reason to clap, you see, because I fixed it. So if it works, then I'm thrilled to pieces. But you see, inside a motor car engine, this reaction is going on thousands of times in a short space of a few minutes. And that, of course, if you said, can that make a car do 100 miles an hour? Yes, definitely. Now, I don't know, and this is the bit I wanted to tell you, it was chemists who about 300 years ago recognized the hugely important value of air in the way that fuels burn. Now, I don't know whether any of you noticed the color of the flame down there. I noticed it, and I'm sure some of you may have. It was actually blue. Now, that blue flame which you saw is an invention of the science of chemistry. And dear children, the blue flame was invented by none other than the great Robert Wilhelm Bunsen, otherwise known as Bunsen. And here it is in my chemistry set from 1958, is a Bunsen burner. And the genius of the Bunsen burner was the air hole here. The gas went in at the bottom, and it was mixed with air. Such a simple idea, and yet it revolutionized, it played a major role in the Industrial Revolution because it enabled us to burn fuels more efficiently. Every one of your gas cookers has a blue flame. Every single gas or oil-fired central heating system has a blue flame. All the flames inside every internal combustion engine are blue. And this is the sign of what we call complete combustion. There were very few people who had seen a blue flame before 1850, and none of them survived to tell the tale. And the reason being that they were all miners who were killed in mining accidents. And there were lots of mining accidents, and it was the great Humphrey Davy who used to lecture, who invented the miner's safety lamp. If you can imagine that flame there blowing in your face the size of a wall, you are not surprised that no one survived to tell the tale. So what I am telling you today, thanks to the science of chemistry, we have discovered or invented Robert Bunsen invented the blue flame, which is what we call in chemical terms complete combustion. There is no smoke, no yellowness, the combustion is complete. Now, to continue with my third magic fire, because as I said, it is my passion, I wanted to explain to you that scientists, once they had made the remarkable discovery of the fact that air is a mixture of gases, this was made about 300 years ago, they rapidly realized that there are two main gases in the air, one of them which actually is the one responsible for burning, and that was called oxygen. The other one they called nitrogen, and they recognized that about 1/5 of the air is oxygen. And then they started to do experiments to make fuels burn better, not by mixing with air, but by trying to mix them with oxygen or get them to combine with oxygen. And I wanted to show you the result of one such experiment, which was a remarkable triumph of the science of chemistry. And it occurred using the most mundane of substances you could possibly imagine, and that is cotton wool. Cotton wool is a natural fiber. It has been known to human beings for over 5,000 years. And we know that cotton was first grown and used on a large scale in India and also in Mexico. But it is India where the great culture of cotton fabric, cotton weaving grew, and for thousands of years, well before it reached Europe. Now, cotton, what is cotton, chemically speaking? Well, it's a very delicate fabric. It's used in clothing, of course, as you know, and for cosmetic applications. And chemically speaking, it's called cellulose. It's a natural polymer which occurs and which is very, very comfortable to the touch and warm to the feel, and that's why it has a great place in our human history. Not to mention the fact that cotton played a huge role in the Industrial Revolution in this country during the 18th century, when cotton weaving and spinning were developed in the Midlands. Now, if you watch carefully, who on earth would think of burning it? Well, chemists thought of burning everything, and this is one of the things. They burnt cotton, you see, and they thought, wouldn't it be wonderful? There it is, it's burning in air. A hugely boring experiment. You see, it's burning in air because air contains only about 20% oxygen, you see. And so this is what we have in complete combustion. It's burning with this sort of a slightly yellowy flame, and there's a tiny bit of ash left, entirely unspectacular, almost like a piece of paper. Now, what I wanted to tell you next is that during the 19th century, during the middle of the 19th century, chemists were experimenting with adding oxygen to different fuels, either mixing it or combining them chemically. And the remarkable result was achieved by two scientists working independently with cotton. And one of them was Asconio Sobrero, who was an Italian, and the other one was Christian Schönbein, who was a German organic chemist. Nota bene, Christian Schönbein was a good friend and colleague of the great Michael Faraday, who delivered teachers' lectures in this precise spot here for over 30 years during the 19th century. So it was Christian Schönbein who actually was the first person who managed to add to cotton some extra oxygen. Now, how did he achieve that? And also, I told you at the beginning that we can frequently recognize a chemical change by a change of color. And yet you say, look, this cotton wool that I've got here looks the same and feels exactly the same as the cotton wool that I had a minute ago. And yet this has got the extra oxygen in, as I will show you in a second. How, therefore, is this different? Dear children, the difference could be seen by weighing it. You see, if you weigh one of those, they weigh 1.7 grams. But this weighs 2.8 grams, one of these, and an extra 1.1 of a gram of oxygen. Now, that is a huge amount of extra oxygen added in. It actually does have some nitrogen as well. And you may say, well, how did they add this? Well, let's first of all see whether it works, of course, because there's no point in talking about the effect if we don't see how it was done, if it doesn't work. So, first of all, let's give ourselves something to talk about. So here, then, is our cotton wool which has had extra oxygen added to it, and let's see how this burns and spot the difference. And as you see, that was an instantaneous combustion. The whole thing burnt very, very, very quickly indeed, and there was virtually nothing left at all, you see. Now that, of course, dear children, is the proof that the experiment was successful. Now, when Schönbein achieved this experiment, he was absolutely delighted. And as I said, Sobrero, they were working separately, one of them with cotton, the other one with glycerine, and they were similar substances, and they achieved this type of result. They thought it was absolutely amazing. For your information, the way this is made is by using a very similar substance to what's used in gunpowder. Gunpowder contains sulfur, charcoal, and potassium nitrate, nitrates. This uses nitric acid and sulfuric acid. You mix them together and you soak the cotton wool for half an hour and you end up with this. So the oxygen comes about indirectly, but then chemists are people who have understood these processes, and that's why they are able to bring about the effects. Now, what I've actually made here is a high explosive. It is, of course, a very, very dangerous substance. It's popular, its name in the industry is called gun cotton, nitrocellulose. It's hugely dangerous. It's used in engineering and in military purposes, and I would love to demonstrate an explosion for you. Unfortunately, that would be far too dangerous. So what I'm going to do instead, I'm going to demonstrate a propulsion, even two propulsions if we're lucky. And what is a propulsion? A propulsion is a directed explosion. An explosion is a rapid release of gases everywhere, forcing something apart. A propulsion, though, is when you direct them in one direction. So I'm going to start off by showing you how to use these to make a simple mortar. It's rather similar to a cannon, and I'm going to propel some ping pong balls, hopefully to the ceiling of our dear Royal Institution. Now, what I have here is a special, it's like a cannon. This is technically called a mortar. And the principle of it is that you burn the fuel at the bottom. When the fuel, which will be gun cotton, burns at the bottom, it releases a huge amount of hot gases, and they will force the ping pong balls to fly, hopefully, to the ceiling. So that's the principle of this. And what I wanted to tell you, dear children, is every time you watch one of those fireworks displays where there are massive shells exploding in the sky and colors, they are all projected from these. Only they're made of thick cardboard, and the shells go up and then they explode in the air. Today, we're not going to explode the shells up there. We are simply going to fire ping pong balls. Now, for this is a steel tube. It's sealed off at the bottom. There is a hole here through which I shall put a fuse in order to light the fuel. And this is what we call a cage, a gun cotton cage, in which we put our strip of gun cotton to enable the fuel to sink to the bottom. So I'm going to take a strip of gun cotton, which I have here. By the way, one of the very important things when doing any experiments with combustibles is to make sure that your combustible is well away from the source of ignition, because otherwise terrible accidents can occur. So here I'm going to put in my fuel, which is my gun cotton, into my gun cotton cage like this. I'm going to then drop it into the bottom, and you should hear it make a clang. You see, if I didn't have this, then it wouldn't fall to the bottom. It has not fallen to the bottom, you see. I can tell that, so we just need to compress it, or I'll take a little bit out. I'll tell you why. I don't want to do too violent an explosion here. We wouldn't want to damage this ceiling here. That would be a great shame. So please excuse me. I've just taken a little bit out. Let's see if it makes a clang. Ah, et voila. Now then, please excuse me. I'm now going to get a small piece of fuse. So I have here, returning to my box, I have here my special fuse powders, which I fuse, like little fuses actually, and I'm going to take a small strip there, and I'm going to put this back in here, taking great care, and now we shall put our fuse in here. Now then, the next thing we shall do, we shall put it like that. We shall now pop in 1, 2, 3, 4 ping pong balls. 4 ping pong balls, and we shall now set up our mortar and fire them almost vertically, maybe at a slight angle, but they're like that, sort of there. Actually, let's fire them up there, approximately. Now, this doesn't always work. Please don't expect miracles. This is only a chemistry experiment, but we will always do our best. We all do our best. All sorts of things can happen, but we'll do our best. Now, please excuse me. I'm just going to move these away there, and hopefully we'll have a launch into the roof here. I'm going to once again take precautions. I've got to put my other flammables away into my box here, and then we shall light and see, and let's hope that this works. So here we are then. Let's make sure the clamp is on. There will be a bit of a bang, by the way, as they shoot out. And if they shoot out, then they will fall down. So if a ping pong ball hits you, please don't worry, dear children. They're very light. Now, here we are. Here we are. Fingers crossed. 3, 2, 1. Et voila. The fizz is burning. The fuse is burning. Fingers crossed that we shall shortly have a projection. A propulsion, rather. Oh, there we are. Oh, I don't... Did they go anywhere? They must have gone somewhere. They're not in here, I tell you. So there were ping pong balls have gone. Did anyone find a ping pong ball? I don't... No, I'm not here. Now, something... Maybe they've got stuck in the ceiling. I don't know. At any rate, they certainly left this. I don't know where they ended up. But now, if you don't mind, I'm going to just do another propulsion, this time on a slightly different principle. I have a rocket here. And it was the great science fiction writer Jules Verne who, writing in the 1890s, predicted that it was possible to fire a rocket to the moon using gun cotton. Now, I'm not going to attempt to fire this one to the moon. He was so impressed with gun cotton. That's the point I'm trying to make. What I'm going to do, though, is I'm going to put 3 strips of gun cotton, and hopefully we can make this rocket take off at least. It's not going to, again, it's a very tricky one to do. Sometimes these rockets don't do anything. Sometimes they explode in mid-flight. Sometimes they go off with such a bang that everyone is terrified. But I think that in the interests of science, it is very, very important to try it out. It was the great Humphrey Davy whose motto was, if in doubt, try it out. So I'm going to try this out now. Please excuse me. There is that. This, I really don't expect this. I really don't expect it to do very much, but it'll certainly make a lot of fire, probably a bit of smoke, and then we'll turn on to something completely different. Now, this is really very dangerous lighting this, so I do have a special long stick here. Now, so I hope you can all see this is our little rocket here, powered by gun cotton, as the Jules Verne. As I said, it may not do much, but let's fingers for 3, 2, 1. There it is, you see. No, that was just the effect. That was just what we wanted. No, please. I'm not here for applause. I have demonstrated the principle, you see, and the principle is that in this case, the fuel is inside, and as the gases come out, so we have action equal and opposite, and the rocket flies off. So I'm pleased to note that this time we didn't lose our rocket, and we have achieved a successful launch. Please allow me now to pull these things away here, and I'm now going to turn to something completely different. And I have this in here. Now, you see, this is a thermos flask. Now, we will all associate a thermos flask with a nice cup, a hot cup of tea, going on a picnic, tea, hot chocolate, coffee, or something like that, you see. And that is what they're normally used for. However, what I wanted to tell you, that I don't have hot chocolate here, or tea, or anything indeed like that. I have something completely different. Please allow me, first of all, to demonstrate. Now then, you see, among magicians, this is popularly called magic disappearing water. And the reason why it's called magic disappearing water, because that's exactly what it does. It looks like water. When we pour it out, it's a colorless liquid. And when we pour it out, it goes like this. And then as we pour it onto our bench, you see, in a very short space of time, it disappears into thin air. Now, the reason why it disappears into thin air is because that's exactly what it is. This, you see what I have, this liquid which I have in here is actually called liquid nitrogen, you see. And it is liquid nitrogen was the result of research by chemists once again in the 19th century. And the history is approximately like this. In the year 1624, the great Flemish iatrochemist Johannes Baptista van Helmont invented the word gas. He invented the word gas from the Greek word chaos, which means disorganized. So people started to recognize that there are substances which are called gases. Until then, it had only been air. By the end of the 18th century, people had started to recognize that air is a mixture of nitrogen, oxygen, tiny bits of carbon dioxide, other gases, sulfur dioxide, had been recognized. Now, once people had identified gases by their chemical properties, they then started to investigate the physics. Now, physics is what this is about, what I'm going to show in the next few experiments, because that too is one of my favorite subjects. Physics is about matter and energy. And once people had started to discover different gases, sulfur dioxide, carbon dioxide, chlorine, they then started, well, can we turn these liquids to gases? And one of the greatest discoveries was made here in this institution. It was in 1823 that Michael Faraday, for the first time, obtained liquid chlorine. Chlorine had been a gas at a temperature of about -30. It turns into a liquid. And after that, the chase was on. Could we turn all gases into liquids? Now, in order to do that, we needed to get lower and lower temperatures. So people tried all sorts of techniques. By about 1860, all the gases had been turned to liquids except for oxygen, nitrogen, and hydrogen. Those three. And those three gases were called the permanent gases. No one could actually achieve the result of turning them into a liquid because they couldn't get the temperature lower. So physicists started racing. Who could get the lowest temperature? Now, the race was won in 1888 by two Polish scientists, two Polish physicists, Olszewski and Wróblewski, who first managed to achieve a temperature low enough to change air into a liquid. Now, nitrogen, liquid nitrogen, has a boiling point, which is here, of -196 degrees centigrade. Now, just to tell you, put that into perspective for you, allow me to tell you this. It was water boils at 100. Water freezes at 0 degrees centigrade. In your deep freezer in your home, the lowest temperature is about -20 or -30. The lowest temperature achieved on planet Earth, about -60. This is -196. That is an amazingly low temperature by any standards in the universe. Indeed, the lowest temperature possible to reach on the universe is absolute zero, is -273 degrees centigrade. Now, the reason, therefore, why liquid nitrogen is boiling here is because this room is amazingly hot compared to liquid nitrogen. It's well above the boiling point. Now, if liquid nitrogen is so cold, then it obviously makes sense to freeze some water, to turn some water into ice. And what I'm going to do now, please excuse me, what I'm going to do now is to pour some water into our beaker here, and then I'm going to cover it with a liquid nitrogen. And we shall watch the water gradually turn into ice. Please allow me just to lower that down here, pop that on there, and there goes our water. So water is being poured here. And now we shall cover the water. Let's just pour a tiny bit on. It's quite a critical one to get an effect which I would very much hope I can show you all. Now, we're going to now pour some liquid nitrogen onto our water and allow the water to start freezing. Now, what you see coming off, that white steam, that what looks like white steam, that's exactly what it is. This is actually steam. It's cold steam, and it's caused by water vapor, which is in the atmosphere, locally being cooled, and therefore making tiny droplets. This is exactly the same as what you see see in fog, in mist, and in clouds, and coming out of the kettle, just at different temperatures. It is tiny droplets of water. Now, please watch carefully and listen as well. I'm going to fill that up. Now, listen to the sound of water freezing while I prepare the next experiment. Now you see, there is crackling. It's crackling. The reason why it's crackling is because water, when it freezes, it expands. This is most unusual in the world of liquids. Very few liquids expand. Water is unique among them. And when the water expands, it sets up huge pressures. The crystals set up huge pressures among themselves, and they move past each other, and they exert mechanical forces. The mechanical forces are very big indeed, and they are capable of making potholes in roads. They are capable of breaking engines apart which have not got antifreeze in them, and they are capable even of possibly shattering this beaker if the conditions are correct. But I shall allow this to continue. I'm going to add a little more, and I shall very shortly come back to this. And when I do, please listen, you may hear a louder crack. If you hear a louder crack, that may be the beaker cracking. It doesn't always crack, but you can certainly hear the crystals as the water expands. Now, while that is going on, allow me to show you another experiment. I have here a piece of rubber. Oh, did you hear that? That was the beaker cracking, you see. So the beaker has now cracked due to the huge forces which the water molecules set up as they expanded, and we shall very shortly investigate the effect of that crack, you see. So I'll just pour some liquid. Oh, we're running out. Not to worry. I do have some more liquid nitrogen here. Please excuse me, just to make sure that it all does freeze thoroughly and properly. Now, as I was saying, rubber is a solid, but it is an elastic solid. If I let it go, it returns back to its normal shape like this, you see. It is most unusual in its elastic. There aren't many natural materials which are elastic. And the reason for this, it's made up of tiny, tiny molecules which store energy. They're like little springs. It's difficult to explain. Indeed, I don't understand it very well myself. But the important thing is, at room temperature, it's quite warm, you see. Quite warm compared to the temperatures out into space and the temperature of liquid nitrogen. And I'm going to now put this into some liquid nitrogen, and I wanted you to observe the effect on the rubber tubing. Please watch carefully. The first thing is this. You'll notice this most curious effect, you see, and that is a spray. There is liquid nitrogen is spraying out of the rubber tube, you see. Now, this is, of course, it looks very entertaining, but there is a very good scientific reason for this. Now, the scientific reason is as follows. You see, we now have established what we call thermal equilibrium. Initially, the rubber tube was very, very hot indeed compared to the liquid nitrogen, and therefore, the liquid nitrogen in contact with it boiled. Now, one of the most important ideas in physics is that when a liquid boils, it changes, its volume enormously expands by a factor of about 1,000. The liquid nitrogen, as it boiled in the rubber tube, turned into a gas and forced the liquid nitrogen out. Now, let us examine what has happened to the elasticity of our rubber tubing. And we take it out, and you see, tap it here, and you notice it has straight away broken into fragments. Now, the reason for this, you see, watch out, it's very cold and you might get frostbite, so I wouldn't hold it for too long, young man. Now, as I was saying, this has now become very, very brittle indeed. Why is that? And it is to do with the most important idea in physics. And the idea is that at high temperatures, there is lots of energy. Everything has lots of energy and moves around. So the rubber tubing is elastic in here because it's warm. However, at low temperatures, the molecules lose their ability to vibrate. They stop behaving in a springy manner, and they lock into a rigid solid. Now, physical changes are reversible. This will warm up, and it will become elastic once again. Now, let's just have a quick look at our beaker and see whether it has cracked. And you'll notice there it is. There's a large crack in the bottom. There's a tiny bit of ice frozen there, and we'll be able to look at that afterwards if anyone would like to see it afterwards. Now, what I wanted to show you next is an experiment which illustrates the huge effect of pressure on the temperature, or the huge effect, yes, of pressure on the temperature, on the temperature of a gas. I have here a balloon which I blew up just before I started today, and it is full of air. And the air in here exerts a pressure on the membrane which is elastic, and that's why the balloon is blown up. However, if we now pour some liquid nitrogen onto the balloon and cool the balloon down, the molecules which we can't see, which are moving around all the time, are exerting a pressure on the balloon. Hence, it is moving around. Hence, it's got this shape. Now, one of the great discoveries of the last century, of the 19th century, should I say, was the idea that molecules move all the time. It's called the kinetic theory, and matter is made of tiny particles which move around. And the best example, if you can all appreciate the idea that even though you don't think its air is moving, you all know that if we closed all the doors in here, made the place absolutely airtight, and I spilt a large bottle of perfume here, and no one moved, you would all be able to smell it within half an hour. And the reason is because the molecules are moving all the time by a process which is called diffusion. This is one of the great ideas. And what I just simply wanted to tell you, though there's no movement in the balloon, but the molecules are moving. Now, if we now cool the balloon down by pouring liquid nitrogen, the molecules have less energy and they move much more slowly. Please watch carefully what happens to the balloon. As I'm cooling it down, the molecules are losing their energy. As they lose their energy, they move more slowly. As they move more slowly, so they exert a lower and lower pressure. And here it is. I have a little more here. Sorry, I knew I'd run out. We're going to try and collapse it as much as I can. As much as I can here. There it is. And now you see, this is a demonstration of the huge change of volume of a gas at a lower temperature. Gases have a huge coefficient of expansion when it comes to temperature. At higher temperatures, they expand hugely, as we saw. At lower temperatures, they contract. Now, watch carefully. Here is our balloon, totally and utterly collapsed. But now let's warm it back up to room temperature. And we could do this by flapping it around, just like this, and throwing it up in the air a few times. And if we now throw it up in the air a few times, then you'll see the shape of the balloon is rapidly restored to its original shape. And this is caused by the fact that the molecules inside have warmed up, therefore they move more rapidly, and they are able to exert a greater pressure. This then is a few of the things. All I wanted to tell you that some of the great research on low temperatures was done by one of the great professors of the Royal Institution, Professor Sir Charles Dewar. In fact, there's a photograph of him in the gentleman's toilets, if anyone happens to visit that later on. But Charles Dewar gave his name to Dewar flasks, or thermos flasks, but he was one of the great physicists, a Scottish physicist, at the beginning of the 20th century, late 1800s. Right, so that then is liquid nitrogen there. And I wanted now, since we're on the subject of an inflated balloon, to turn to another type of physical property that has been investigated by scientists for many, many, many centuries. And this is the idea of the
compressibility of gases. Now, this topic was particularly studied by the great Irish chemist Robert Boyle at Oxford University. He was a natural philosopher, actually, Robert Boyle, and there were a whole bunch of amazingly bright people working alongside Robert Boyle at Oxford University in the 17th century. Robert Boyle investigated the change of volume of a gas with pressure. If you double the pressure, you halve the volume, etc. Now, what we have been able to do today, we have been able to exploit these laws by understanding how to use air and compressing it and expanding it. All gases are easily compressible. Now, in nature, how does that work? Well, birds fly. Birds fly. When a bird flies, it flaps its wings, and the wing presses against the air, which provides upthrust, and hence the bird can fly. Now, humans have been trying to fly for thousands of years, and as you know, only in the last 100 years have we actually made aeroplanes, man-made machines that fly. One of the great triumphs of the science of physics and of chemistry and engineering and so forth. So that makes use of the ability of air to exert an upthrust. I wanted just to show you a couple of very simple inventions and toys. It's really quite pathetic almost, just to illustrate, though, how the compressibility of air can be exploited in so many ways. I have here a little balloon helicopter. Look, these cost £1. Anyone can buy them. And it works on the principle that you blow up a balloon like this. Now you connect it to a little propeller. Now this is made of a plastic, it's a polymer, it's very light and very strong, and it has got little ducts in it, little ducts like that. And if we allow this to fly, then there it is, flying up beautifully there, just at the right level, you see. So there is our little toy. Now that's making use of the idea that air is compressible in two ways. One is the means of propulsion, which is the balloon squeezing the air out, and the second one is making the propeller blades push against the air below. Now, what about air compressors? Did you know, dear children, that we all have an air compressor? It's our lungs. It's our lungs. Every time we breathe, we take air in and then we blow it out again, you see. Now, we as humans are very clever because we've said, oh, look, we breathe, but we breathe because we need the oxygen. We don't know about that, but that's what chemists have discovered. So why don't we make use of the air where we blow it out? What's the point of just blowing it out? We can make musical instruments. So a whole load of instruments have been invented where we make use of the pressure in our lungs to actually play a tune. So I'm just going to play you a simple tune on this just to show you once again an application of compressed air. And there you see a very, very simple tune. No, I'm not here for a thing. I'm merely illustrating. Now, what about football? The world's most popular game at this moment being played by tens of thousands of people all around. Why does the ball bounce? Because it is full of air. Air is compressible. The rubber football, this got a rubber bladder inside, was invented in 1855 by Goodyear, and indeed today Goodyear's tires are still well known throughout the world. But that was exploiting the fact that air is compressible. What about your comfortable rides in your motor cars or your bicycles? Why are they comfortable? Because they've got tires. What are the tires filled with? Air. Air is compressible. This is one of the most important ideas in physics, and it is hugely, hugely important in the technology of pneumatics. Now, I'm not going to go into the details of the technology of pneumatics, but I'm going to return to the topic now of the composition of air. You will very shortly in school, you'll be going into your school and you'll be told in your science lessons that air is a mixture of gases. 78% nitrogen, 21% oxygen, 1% argon, neon, krypton, xenon, helium, radon, 0.04% carbon dioxide, small amounts, variable amounts of water vapor. You will learn that list off by heart. You will go to your chemistry test, you'll get 10 out of 10, say, wee, I'm brilliant at chemistry, I got 10 out of 10. No. You're not brilliant at chemistry. You've actually learned a list of names very well, but have you understood them? And this is what science is about. Science is about understanding. And what I wanted to tell you today is the fact that it has taken thousands of years to discover that air is a mixture of gases. Allow me to show you an experiment which is very familiar to everyone here. And I wanted to tell you that air is the idea that air is a single substance or an element was one of the most important ideas in science for thousands of years. There were just 4 elements according to the Greek philosophers, the great Greek philosophers. Please allow me, I'd like to put this on top here. I do want everyone to see, so if you excuse me, at the expense of wasting another couple of seconds, I just wanted to see so that everyone can see. Here is a candle, and I'm now going to put the tumbler over the candle. Now, if I put the tumbler over the candle, you see, you'll all say, okay, the air's gone out, the candle flame goes out, you see. And everyone's, well, the candle flame's gone out because it's used up all the oxygen, you see. Now, that's very easy to say that today. Did you know that this experiment was first explained, or was first described by the great Greek mechanician and engineer Philo of Byzantium about 200 BC. This is 2,200 years ago. He described this experiment, but he didn't explain it. He said, I don't know why. That explanation was later repeated by other people. The demonstration was repeated, but no one explained. They said, look, it's air in here. Air's an element. We can't, and we don't know. It took 2,000 more years almost before that explanation was made that air is a mixture. Allow me to show you this. Here I have 2 jars, and if I say to you which one contains a mixture, one contains a single substance, you say that's a stupid question. This one contains a single substance because all the beads are white. This one contains a mixture because the beads are white, black, red, and green. So that's a stupid question. However, I have another question for you now. I have here 3 jars. And if I tell you that one of these jars contains oxygen, one of them contains nitrogen, and one of them contains air, which is a mixture, can you tell me which is which? No, you can't. No, you can't. And you see, because does air look like a mixture? Does it? No. To prove that air is a mixture, and this is the point, it took thousands of years in experiments involving combustion and respiration. Please allow me now to show you the simple test. You can decide for yourselves which one is air, which one is nitrogen, and which one is oxygen. We dip the flame in one at a time, put it in there, we put it in here, and we put it in here. Oh, easy. Wasn't that easy, you see? But this is the point I'm trying to tell you. To make this discovery took thousands of years. The greatest minds on our planet all put together. Now, having showed you this and having made to you the point of the importance of the discovery of oxygen, it is of course necessary for me to show you another experiment with fire. You must excuse me, but in this particular case, I wanted to show you how scientists can make pure oxygen in the laboratory and how this oxygen can then be used to make a fuel burn better. I'm going to start off with a very mundane experiment. The experiment I have here. And in this experiment, I'm going to burn some alcohol, ethanol as it's known. It's been known for many, many hundreds of years. It was first distilled by the Italians in about 1150. There is alcohol. It's made naturally by fermentation during the fermentation processes, and people have been making alcoholic beverages for some time. Now, I'm going to show you this experiment here, and I just wanted you to observe it burning. I have to warn you, this is dreadfully boring, but for the purposes of comparison, we must see what we were started with. So this is how alcohol burns. It's a flame which you can barely see, and I'm going to now just extinguish it. I'm going to extinguish just by removing the air. You see, we exclude the air, and so it has been extinguished. Now, you must excuse me. I've just felt a little bit of something. I have not told you, but I do have a minor problem. I suffer from something which is called acute dehydration syndrome. And that means that occasionally I faint because I've got lack of water, especially if I'm talking a lot. And if you don't mind, there is a perfect, everyone is alerted there. The emergency services know about this. I have to have a cup of tea, you see, and I should have had it 5 minutes ago because so if you don't mind, I do have to take my tea because otherwise I may faint. Now, sometimes, by the way, when this happens, I faint. You must understand I do make a full recovery and people do know how to deal with me. So you must not be too concerned if you see me feeling faint or losing my control of what I'm trying to say. But I am at the moment still good. I think I am. Now, please, if you don't mind, I wanted now. I've just the water is boiling. Once I've had my tea, I should be in a much better position. I wanted next to show you how to make pure oxygen in the laboratory, how this is made by pupils in schools and what we learn about it. It is made from this liquid which I have in here. This is a solution of hydrogen peroxide. The formula for hydrogen peroxide is H2O2. Water is H2O, this is H2O2. This is an extra oxygen atom added in. And if I pour some here, then we can put it in. We can release oxygen. If you don't mind, I think the tea is about to be made. Not quite yet. I really must keep in touch. Now, what I wanted to show you is hydrogen peroxide does release pure oxygen. And I'm going to show you, first of all, that there is no oxygen present here. I'm going to take this splint here, and I'm going to show this is air. There is oxygen, of course, but only in air. 20. See, put that there, there, there. And it does nothing, you see, because there's no oxygen. Make it glow. There, no, not pure oxygen, just air. However, we can release pure oxygen. We can release pure oxygen by adding some potassium permanganate. Now, if we could have the lights off, please, for this. I'll tell you when, not just yet. Let's put some in, and then I will show you pure oxygen, how it affects the burning splint. There we are. Lights off, please. The splint goes in. And watch again. Et voila. You see? And this is how oxygen is produced in a laboratory, by the reaction or decomposition of hydrogen peroxide. And there you see, beautifully. Could we have the lights back on? Now, what I wanted to tell you is that we can combine, during the Second World War, scientists were working on producing a more efficient rocket fuel to project missiles right across the continents. Excuse me. It's just boiled. I must have my tea because otherwise I'm definitely not going to make it to the end. I can feel my legs beginning to wobble. I do take this tea regularly. This is normal, so please do not be too concerned. I just need to take... I've just realized I've forgotten to bring my milk. Oh dear, this is very embarrassing. This wasn't meant to happen. I do apologize. Let me just, oh dear. I'm going to burn myself, I think, so you must excuse me. Let's just put this down here. I'm going to have to drink it because I really am not very well, so you must excuse me. I burnt myself. Someone said use liquid nitrogen. Exactly. If in doubt, try it out. Please excuse me. I'm going to call... No. This is necessary. I don't know whether it'll work, but I think it's very important. No. I'm now going to put science into practice in my teapot now. I have a teapot, you see, and I have got liquid nitrogen, and hopefully I will now be able to drink the tea, you see. So if you excuse me, I will be able to hopefully make a full recovery and continue with my experiments. So please allow me, just getting to the end here. Oh dear. I think it'll be much more. Do you know, it's so much better. It's perfect now. Thank you very much. Listen, I really am fine now. I've totally recovered, and I can now continue. I was telling you about during the Second World War, scientists were attempting to make a more powerful fuel. Now, these were German scientists working for the Nazi regime, and they were trying to make a liquid rocket fuel which would propel to a much more efficient fuel than powders which had been used until then. And they used this mixture, they thought of using this mixture of alcohol combined with hydrogen peroxide, which would release oxygen. And that's what I intend to show next. Now, it doesn't always work, but I just want to show the sort of effect. They mix these two together, you see, and then once they have mixed them, they then add some, we then add potassium permanganate. So we've mixed together alcohol as a fuel, hydrogen peroxide as an oxidant, and we are now going to set fire to it, which will just burn normally, because there's no oxygen being produced, if it burns at all. There it is, it's burning. However, if we now release some pure oxygen from inside, watch what happens. And there you see a range of wild noises and you see the huge amount of energy being released just by that. Now, it was this specific experiment, you see, which they said amazing energy, and they, in fact, used this mixture to propel V-2 rockets. It was the first example of military use of liquid-powered fuels during the Second World War. Fortunately, it came too late to do any lasting damage or to affect the outcome of the Second World War. Now, what I wanted to move on to now is a topic which is very close to my heart, and that is the topic which concerns this. And that, of course, is plant gas. You see, every beautiful plant that grows on this planet actually is made from a gas. It's made from a gas. It's made from a gas which we find in the atmosphere, in a very, very, very small amount. The gas is called carbon dioxide. Now, this is a famous apparatus. It was obviously invented by one of the great German chemists, whose name was Kipp, obviously, and it's very clever indeed, because it allows a gas to be produced from a reaction of a solid with a liquid, and this clever mechanism, clever bulb arrangement. Now, what we have here is we have, in the top bulb, we have is connected to the bottom bulb by a tube which goes through the middle. The liquid in there, which you can see is a colorless liquid, is called hydrochloric acid. It's one of those acids. It's a strong mineral acid. And what we've got in the middle is some marble chips called calcium carbonate. Now, I'm just going to light, and what I wanted to tell you is that carbon dioxide, there is a tiny amount in air, 4 parts per 10,000. Now, the amazing thing that I find, all the plants in the world are actually made from carbon dioxide. And chemists have discovered this and they only discovered this reaction just over 100 years ago. It's called photosynthesis. It's where the carbon dioxide from the air combines with water in the cells of the plants. They're green, you see. You notice how green leaves are everywhere present on plants. They contain chlorophyll, the coloring matter, and that enables this reaction. It's the chlorophyll which enables this reaction to take place in a reaction called photosynthesis. The action of light generates this production of these large molecules which plants are made of. Now, what I'm going to do is this. I'm going to show you how to make, and also, I also wanted to tell you, dear children, that carbon dioxide gas is actually, you all drink it. You see, in any fizzy drink. I have here a bottle of fizzy mineral water, you see, and the reason, oh, there it is, it's okay, it's fizzy, it's got carbon dioxide in, and I'm going to have a little drink if you don't mind. It's bubbling away because it's got, and I'm drinking your good health. Please excuse me, that was very necessary. Now, what I'm going to do now, so I've had my drink of carbon dioxide in water, and I'm now going to set forth my generator for making some carbon dioxide. So I open my tap, the acid will go from the top bulb to the bottom. From the bottom, it will start reacting and it will start fizzing. Now, as it starts fizzing, the carbon dioxide gas will be released from our pipe, and this is what I wanted to tell you. Carbon dioxide gas is heavier than air, so it sinks to the bottom, and it does not support combustion. So that means that when we lower our burning splint into the carbon dioxide, then it should go out, because carbon dioxide smothers the oxygen. This is surrounded by air, you see, and in which there is oxygen, but you see, carbon dioxide smothers the oxygen, and there it is. It's not going out yet fully. Hang on, I'm going to open this a little bit more. Sorry, I had it virtually. I'll just push it once again, and let's watch carefully as the carbon dioxide should smother the flame as it gets lower and lower. It's denser. It's not doing too well. Something is not quite right. I'm not 100% happy. Please allow me just to come around, just to make sure that I've undone. There is sometimes these tubes, they get a little stuck. Let me try once again, and we'll see what's going on. I'm not 100% happy with this at the moment. Let's see though. Ah, that's more like it. Please watch carefully. We're now making large amounts of carbon dioxide. The flame goes out. See, we're almost full. Now, to show you even more convincingly, I'm going to try and blow a soap bubble and make it float on here. It's very difficult, by the way, but there's a bit of a draft in here. Ah, almost. Yes, we almost did it. Let's just try once again. That's not very good, is it? Missed. There we are, surely. Yes, we have two bubbles. You have some bubbles floating. Now you see, that is showing carbon dioxide denser than air. Now please watch carefully. Regardez attentivement. And there you see, no, I'm merely illustrating for you the principles of science. Now, we have now finished some experiments, and we're now coming on to our final two experiments, which I have here. And I have two balloons. One of these balloons is filled with the lightest gas in the universe. That gas, of course, is hydrogen. Hydrogen, the name was given by the great French chemist Antoine Laurent Lavoisier, and it is composed, the word itself is made up of two words, hydra and genesis. Hydra in ancient Greek meaning water, genesis to be born. So it is that gas which, when it burns, it makes water. In chemical symbol terms, 2H2 plus O2 makes 2H2O. So I'm going to ignite the balloon filled with pure hydrogen, and the final experiment, I will be igniting a mixture of hydrogen with the gas which makes things burn better, which I very much hope all know is called oxygen. And that, of course, that will be my last experiment. So here we go then. This then is hydrogen gas burning. It makes a little bang. It's not a very loud bang. Makes a moderate bang. And there's a little sort of orange flame that you can observe, and a puff of steam maybe. So here we go. This is pure hydrogen. There it is. And now, I am now coming to the final experiment. This will be the last experiment in today's demonstration, and I very much hope you've enjoyed learning something about the achievements of the science and the history of science, physics, and chemistry, and their applications. And this contains a mixture of hydrogen and oxygen. Now, this mixture is really used to propel space rockets to the moon. This makes a very loud bang indeed. So if you're terrified, you should put your fingers in your ears. So this will be my final experiment, a mixture of hydrogen and oxygen. Everything I wanted to show you. I very much hope you've all enjoyed yourselves, and I hope you've all learned some chemistry. Thank you very much indeed. Thank you very much indeed. I hope you've all enjoyed learning about the science, chemistry, and the science of physics. Thank you very much indeed. Thank you very much indeed. Thank you. Thank you very much, children.